So today we are going to start our third module. In third module, what we are going to discuss is all about different modulation techniques. Different modulation techniques that is being used for wireless communication. According to the syllabus, the first part of our third module deals with digital signaling for flat fading channels. What are flat fading channels? In the second module, we have discussed what is flat fading model or what is a flat fading channel. What is flat fading and what is frequency selective fading. So according to the syllabus, we have digital signaling for flat fading channels, analysis of average error probability, outage probability of BPSK in flat fading channels. In the previous classes, we have seen how to calculate the average probability of error. And we have also understood that the average probability of error is one of the important measures to understand the capacity of a wireless channel. Not only for the capacity, the efficiency of a channel also depends upon the probability of error. In the next case, in the next part, we will be studying about the probability of a BPSK modulated signal not properly received in the receiver's end. That is called as outage probability. The power received at the receiver's end is much less than the required power for reception. The threshold power should be optimal. So what are the chances? The outage probability of BPSK in flat fading channel means what are the chances that a signal is not received with the required power at the receiver's end when it is BPSK modulated, and what happens when it is in a flat fading channel model. What are flat fading channels and what are frequency selective channels? We have discussed about this in the previous module or in the previous sessions. You remember? Can anybody tell me what is coherence bandwidth? When the coherence bandwidth is less than the So when do we have these flat fading conditions? As the demand grows for digital wireless communication systems, the accurate prediction of average and instantaneous bit error rates BER for different modulation schemes will become increasingly important in system design. The bit error rate predictions will not only provide an understanding of the performance of each modulation method in the operating environment but also reveal the limits of data rate and channel capacity. So here what we are saying is that why we are going to study all these things. What are the analysis that we are going to do? How we are going to analyze the performance of a wireless channel in different modulation schemes. In the coming lessons, we will be learning different kinds of modulation schemes like OFDM, and we have a very new kind of modulation system recently invented, OTFS, orthogonal time frequency space modulation, OTFS. We have OFDM in our syllabus. So what we are going to study now is the different modulation techniques and the probability of error, the performance analysis of different modulation techniques in a wireless channel. And here we are going to study is in a flat fading channel. Now what is the probability of error in BPSK? In the 6th semester, while studying analog and digital communication, we have studied the derivation for probability of error in BPSK and QPSK. We have revised that, and I believe that it has also come for your university exams, and you have written that what is the error probability in BPSK, average error probability in BPSK. So we'll make a study of that with different, in a slightly different context. The signal to noise ratio, as we have seen, gamma, its relation to energy per bit EB and energy per symbol. Energy per bit EB, energy per symbol ES. And how it is related to signal to noise ratio. Signal to noise ratio, SNR per symbol is given by EB by N naught, where N naught by 2 is the power spectral density of the signal. Gamma B, energy per bit EB by N naught. This is how we calculate signal to noise ratio per symbol and signal to noise ratio per bit. So the probability of error PB is equal to Q function of root of 2 EB by N naught. Or in other words, when you substitute signal to noise ratio, you get Q function of root of 2 signal to noise ratio per bit. So let us do a very small problem. What is the bit error rate of a BPSK communication over AWGN communication channel at the signal to noise ratio SNR-dB, where it is given as 10, that is gamma is 10. So very simple, we are calculating, converting this from dB to bits, and then we are substituting this into the function what we have derived right now, Q of root gamma. Gamma is the signal to noise ratio. So when we do like this, you get Q of root 10, and using the Q function table, when you solve it, you will get 7.82 into 10 raised to 4. This value is determined by a Q table. It is available in your textbooks. You can use the Q table for your exams also. Average probability of error. The average probability of error is used as the performance metrics. Do you remember what are the other performance metrics that we use to measure the efficiency of a channel other than the probability of error? We have discussed about this in the previous sessions. The average probability of error is used as a performance metric when Ts is approximately equal to Tc, where Ts is the symbol time and Tc is the coherence time. In that case, the average probability of error is computed by integrating the error probability in AWGN over fading distribution. Do you remember what is Rayleigh fading and Rayleigh distribution? We have studied about that in probability distributions. So here we will be having a practical application of Rayleigh fading distributions. So probability of error Ps is equal to integral 0 to infinity Ps of gamma P gamma S of gamma d gamma, where P S of gamma is the probability of symbol error in AWGN channel with SNR gamma. So for a given distribution of the fading amplitude R, P gamma S of gamma d gamma will be equal to PR dr. Here we will be considering the distribution in flat fading channels. The probability distribution function will follow Rayleigh fading mechanisms or fading path. This distribution of the wireless signal will be in the Rayleigh distribution path. So in Rayleigh fading, the received signal amplitude R has a Rayleigh distribution, and Rayleigh distribution is given by P of R is equal to R by sigma square e raised to minus R square 2 sigma square, where R is always greater than or equal to 0. And the signal power is exponentially distributed with mean 2 sigma square. So in that case, SNR per symbol, signal to noise ratio per symbol, for a given amplitude of R will be given as gamma is equal to R square Ts by 2 sigma n square. Like what we have done for Gaussian distribution, the same thing we are going to do here for Rayleigh distribution. So the variance sigma n square is equal to n naught by 2 is the PSD of the noise in the in phase and quadrature branches. Differentiating both the sides, sigma n square is equal to n naught by 2 d sigma. Differentiating both the sides in signal to noise ratio, we get RTS by sigma n square dr. Now we are substituting the value for d gamma, signal to noise ratio, in the previous equation, in the first equation. On substituting, what we'll get? P gamma S of gamma is equal to sigma n square by sigma square Ts e raised to minus gamma sigma n square by 2 sigma square Ts. We are substituting these values in Rayleigh distribution. In that case, what we'll get? We'll get the average SNR per symbol, that is gamma S is equal to sigma square Ts by sigma n square. So the probability of SNR gamma S to be gamma, that is equal to 1 by gamma S e raised to minus gamma by gamma S. The average signal to noise ratio per symbol. You should understand that we are calculating SNR per symbol here. So we have derived that P gamma S of gamma is equal to 1 by gamma S e raised to minus gamma by gamma S. For a BPSK signal, P gamma B of gamma is equal to 1 by gamma B e raised to minus gamma by gamma B. Probability per bit. Why for BPSK we are considering it as a, because per symbol we have only 2 bits, right? The probability of error for a BPSK modulated signal is thus given by PB is equal to Q root of 2 EB by N naught, which is equal to Q root of 2 gamma B. So the average probability of error for BPSK in Rayleigh fading is given by PB is equal to 1 by 2 1 minus root of gamma B by 1 plus gamma B, that is approximately equal to 1 by 4 gamma B. Derive the equation for average probability of error for a BPSK signal in a Rayleigh fading channel or in flat fading channels. A question may come out of any of these things. Derive the equation for the average probability of error for a BPSK in a flat fading channel. This is the derivation. Okay. Derive the average probability of error BPSK for a BPSK signal in Rayleigh fading. This is the derivation. And this derivation is extremely important to you for your exams. I'm repeating that it is extremely important for your exams. So we have seen the first part of the half of the first part of our third module. The next thing what we are going to study is outage probability. What is outage probability? Performance of a digital transmission is usually measured in terms of average probability of bit error. In fading channels, the signal amplitude can exhibit erratic behavior and an average performance measure may not be meaningful. An alternative measure of performance under these conditions is the probability of outage. So we have 2 important measures. One is that average signal to noise ratio, which we have just calculated. The second one is the probability of outage. Definition for outage probability. The outage probability relative to gamma naught is defined as P out. P out is the outage probability is equal to P gamma S is less than gamma naught, which is equal to integral 0 to gamma naught P gamma S of gamma d gamma, where gamma naught typically specifies the minimum signal to noise ratio for acceptable performance. So this particular slide gives you two definitions. One is the outage probability and the other one is the gamma naught, which is the minimum threshold signal to noise ratio that is required for average acceptable performance. Gamma naught signifies the minimum signal to noise ratio that should be at the receiving end so that the signal is properly deciphered. The objective of our communication system is that the received signal should be deciphered properly to be understood. So gamma naught is a very significant definition. Gamma naught tells you what is the minimum signal to noise ratio that is required so that the signal is properly received in the receiving end. The outage probability P naught is defined as the probability that gamma S falls below the given value, below a given value. That value is called as gamma naught. Below a given value corresponding to the maximum allowable PS. So as we have seen in the previous slide, we will be seeing for a BPSK signal in a Rayleigh or a flat fading environment where gamma B is expected to be somewhere less than 7 dB. If it is less than 7 dB, it would be declared as an outage situation where the signal cannot be properly received. So we have this gamma naught to be 7 dB in a Rayleigh fading environment. So now we are going to calculate the outage probability, or we are going to derive the equation for the outage probability. In that case, P out is equal to 0 to gamma naught 1 by gamma S e raised to minus gamma S by gamma d gamma S. That is equal to, this gamma S is gamma naught, right? That is equal to 1 minus e raised to gamma naught by gamma S. So the average outage probability P out is equal to 0 to gamma naught 1 by gamma S e raised to minus gamma naught by gamma S d gamma S, which is equal to 1 minus e raised to minus gamma naught by gamma S. From this we are going to calculate the average SNR. In that case, gamma S is equal to gamma naught by minus log 1 minus P out, outage probability. So in terms of decibels, 10 log gamma S must exceed, this is the received signal to noise, this is the signal to noise ratio, this is the threshold signal to noise ratio gamma naught. So in that case, FD should be equal to minus 10 log minus ln, natural log 1 minus P out. In order to maintain the acceptable performance more than 100, 1 minus P out percentage of time. This quantity FD is called as dB fade margin. Define fade margin. FD is equal to minus 10 log minus natural log 1 minus P out. So what is the definition for fade margin? There is a small problem. We'll do this problem and then we'll leave. Determine the required gamma B for a BPSK modulation in slow Rayleigh fading such that 95% of the time or in 95% of the locations the probability PB of gamma B is less than 10 raised to minus 4. So let us see how we are going to solve it. For a BPSK modulation in AWGN, the target bit error rate is obtained at gamma B is equal to 8.5 dB. In that case, we are going to calculate the probability PB of gamma B, which is equal to Q of root 2 gamma B. Here, on substitution, what we'll get gamma naught is taken to be 8.5 dB. So we want the outage probability to be P out to be 0.05. In that case, gamma B is equal to gamma naught by minus ln 1 minus P out. We know the value of gamma naught. We are not taking in dB, okay, so we are converting it into by using 10 to the power. Otherwise, what we'll do is that we'll take 10 log to the value now here, and so you will get it as 21.4 dB. So with this, we have covered 3.1, the first part of the third module.